So we've been acquainted with our del operator, and we've looked at divergence, gradient, and curl. Now let's look at some combinations of different operations. And this comes from section 5 of chapter 16. And one of the first things you'll be able to do is to perform operations of del on multiple vectors or scalar fields. So for example, if we have a product of a scalar field and a vector field, you'll know how to take the divergence of it, the curl of it. You'll also be able to take the divergence of cross product and so forth. And these are actually these are known, the relationships between the left and right hand sides of these equations are known as vector identities. So if you go online and search for vector identities, you'll see a large number of these. And there's more in the textbook that you can refer to. The second objective that you should keep in mind is after viewing this videos, you'll be able to perform multiple operations of del on a single vector or scalar field. For example, here's a curl, and we're taking the divergence of a curl, and here's a gradient, and we're taking the curl of that gradient. So let's look at the first topic, in which we're uh, op, doing multiple operations, or sorry, a single operation on a couple of fields. So the first one is, let's look at the divergence of just a scalar quantity times vector u plus another scalar quantity times vector v. And one aspect that you should know about this del operator is it's a linear operator. So the divergence of the sum of two vectors will equal the sum of the divergence of those vectors. So we have alpha times the divergence of u plus beta times the divergence of v. Another example, let's consider the divergence of a scalar field, u times v. So this is a scalar field. And this contrasted with alpha and beta, which were just constants. And because they were constants, when we take the divergence of those constants, they're equal to 0. So the constants come right out of this divergence on the right-hand side. But when u varies in space, then the divergence of u times v is equal to the gradient of u. We have to apply this del operation on u, and it's the grad u. The application of this del operation on u becomes grad u, and then this becomes a dot product of grad u and v. That's the first term. And the second term is the scalar field u times the divergence of v. So this operation follows the product rule of differentiation. And note that we're simply taking the divergence of a vector, and so the result is a scalar quantity. We have the divergence of two vectors for the first term, and then just the divergence of one of the vectors times u being the second term. And another case, and actually let's look at an example of that, come to think of it. Here we go. So suppose let's say u is equal to, say, x squared plus z squared, and vector v, varies only with y, and it has only an x component and a z hat or a k hat component. Okay, so let's look at the left-hand side of the above equation. So the divergence of u times v is equal to the divergence of x squared plus z squared, again that was u, times v, which is y, and it's in the I hat direction, plus y in the k hat direction. So remember, the divergence is the partial derivative with respect to x of the x component of the vector, and the x component is, so we have partial with respect to x of the x component, and that's x squared plus z squared times y, and then we have to add the partial with respect to y of the y hat component of this vector, and there is no y hat component. It's just has an x and a k hat component, so that's 0. And then we have the partial with respect to z of the z hat component, and that's x squared plus z squared times y. And that is equal to, the first term is equal to 2xy. The second term is 0, and then the third term is 2zy. And if we simplify that, that's 2y times x plus z. And we better check that it's a scalar field, because again, we're taking the divergence of a vector, which results in a scalar. So that was the left-hand side. Now let's look at the right-hand side of this equation. So this was the left-hand side, and this is the right-hand side. So let's confirm that this vector identity is correct. So the left-hand side is the gradient of u. So we have to take the gradient of x squared plus z squared, and that's a vector, remember, and we have to take the dot product with vector v, which again is y I hat plus k hat. And the second term is u, which again is x squared plus z squared, times the divergence of our vector, y I hat plus k hat. Okay, so let's evaluate this first term. The gradient of a scalar field is again the partial derivative of the field with respect to x in the I hat direction, and that gives a 2x in the I hat direction, plus the partial derivative with respect to y in the j hat direction, and that term is 0, plus the partial with respect to z in the k hat direction, and that's 2z. So that was our gradient of our scalar field u, and we're taking the dot product with y I hat plus k hat. And then the second term is u times the divergence of this. So the divergence is again the partial derivative with respect to x of the x hat component, which is 0, and there's no y hat component, and then finally we would have the partial derivative with respect to z in the k hat direction, and that's partial derivative with respect to z of the k hat component, and that's 0. So the second term is equal to 0. So we're left with just one divergence of two vectors, the first vector being, again, the gradient of the scalar, and the second vector being our vector v. And that is equal to 2xy. Again, we're just multiplying the I hat components, and we have to add that to the k hat component, and that's 2z zy. And so again, that's 2y times x plus z. And we therefore have verified this vector identity by evaluating the left-hand side and showing that it was the same as the right-hand side of this vector identity. So let's look at a cross product of a vector, and that vector is the scalar field multiplied by vector v. And following the product rule for differentiation, we apply the del operator to the scalar field first, which again is a gradient, and then we take the cross product of that with v plus u times, we just apply the cross with the cross product of del with v, and that gives a third vector identity. So those were combinations of scalar fields operated on with, combinations of scalar and vector fields operated on with a single operation of del. Let's actually just one more example. Let's look at a vector field dotted with a, well, let's look at this operation. So it's u dotted with the gradient of a vector field. This is really I guess if we were to apply the grad or this del operation with v, that would be a gradient of a vector field. But what this turns out to be is we can separate this dot product operation, as I've drawn here, with the vector part. And if we write that out like this, it looks like that. And just by applying our typical rules of actually distributing this operation to these three different terms, this is u times grad of vx, okay, and in the I hat direction, plus u dotted with the gradient of vy in the j hat direction, plus vector u dotted with the gradient of vz in the k hat direction. Right, so in other words, this would be u. This term would, if we take the dot product between these two vectors, we have ux times the partial of vx with respect to x, plus uy times the partial of vx with respect to y, plus uz partial of vx with respect to z. And that's in the I hat direction. So this is this term right here. And then the second term, we would we would do something similar to the second term, except for we're taking the gradient of vy. And it would have a component in the j hat direction, plus the third term, which is the gradient of vz times the dot product of u times the gradient of vz in the k hat direction. Okay, so those are operations involving multiple fields. Now let's look at, so that was our sort of first objective, performing operations of del on multiple vector and scalar fields. So let's address our second objective of applying multiple del operations. And so the first very important operation is del squared. And that is an operation defined by del dotted with del. So these are two vector operations, and when we dot two vectors together, we get a scalar quantity. And we can think of writing that out as I hat d by dx plus j hat d by dy plus k hat d by dz dotted with the same vector operation. And again, we would apply I hat d by dx with every term in the second parentheses. But when we take the dot product of I hat with j hat and k hat, those terms are 0. So the only term that's left is when we take the dot product of I hat with I hat. So we have I hat dotted with I hat, and we have the second derivative with respect to x. And then likewise, we would multiply the second term with each of the three terms in the second set of parentheses. And the only term that remains non-zero is when we take j hat dotted with itself, and that involves the partial derivative of y operated on the partial derivative with respect to y, and we get a second derivative with respect to y, and so forth. And of course, these dot products all become 1. So the Laplacian, this del squared operator, is the second derivative with respect to x plus the second derivative with respect to y plus the second derivative with respect to z. So when we take the Laplacian of a scalar quantity, and just like to remind you that that's the same as taking the divergence of the gradient of a scalar quantity, right? It's the divergence, or it's the dot product of these two vector quantities operated on this scalar quantity. That's the second derivative of u with respect to x plus the second derivative of u with respect to y plus the second derivative of u with respect to z. The Laplacian of a vector quantity, v, is equal to, we can describe that as the Laplacian on the x component of v times x hat plus the Laplacian on the y component in the j hat direction plus the Laplacian on the z component in the k hat direction. And for example, if we just write out this first term, that would be the second derivative with respect to x of vx plus the second derivative with respect to y of vx plus the second derivative with respect to z of vx in the I hat direction, plus we could write out the Laplacian of vy in a similar way, and so forth. And you should note that this is a vector quantity. Because we're taking a Laplacian of a vector. The Laplacian of a scalar is a scalar quantity. So I'd like to show just two more identities. If we take the divergence of a curl of a vector, then that's always equal to 0. That is, the curl has no divergence. A curl of a vector has no divergence. We could take the curl of a vector, and that vector is the gradient of a scalar, and that's equal to 0. That is, the gradient of a scalar is not rotational, right? The curl, remember, tells us how quickly a given point is rotating, and if the curl is 0, then there's no rotation. So the gradient of a scalar field has no rotation. So let's consider an example. Say we have a scalar field that varies in x, varies linearly with x, and it decreases exponentially with y. So it right. So there's a dependence of e to the minus y on this scalar field. And let's consider taking the Laplacian of the scalar field. And that again is the second derivative with respect to x of x e to the minus y plus the second derivative with respect to y of x e to the minus y plus the second derivative with respect to z, which is 0. And evaluating each of those terms, the second derivative, well, the first derivative of x is 1. The second derivative of x is 0. So now let's look at the second derivative with respect to y of this of u, and I'm going to break that up into a derivative of the first derivative, and so that is going to equal the partial with respect to y of the first derivative of that, which is minus x e to the minus y, and that's the derivative of this with respect to y is plus e to the minus y. So it turns out that the Laplacian of u in this, for this particular field, is equal to u. When we took the Laplacian, we got the same function back. So now let's consider the curl of the gradient of u. So that's the curl, and the gradient of u, remember, was just right. So the gradient of u was the partial of u with respect to x plus the partial of u with respect to y, and then the partial of u with respect to z was 0 again. And that is the curl of the partial with respect to x of u is just e to the minus y. Oh, and I forgot, got to remember that these are, this is of course the gradient is a vector quantity, so I have to make sure I have my unit vectors here. I can't forget those. Okay, so the partial derivative of u with respect to x is e to the minus y, and that's in the I hat component, plus the partial of u with respect to y is minus x e to the minus y in the j hat direction. And so to take the curl of that, remember we set up a matrix with our base vectors on the top row, and then our individual partial derivatives of del in the second row, and then our vector, the different components of our vector in the third row. Right, so this is our vector. So we're taking the curl of our vector. And the x component is e to the minus y. The y component is minus x e to the minus y. And the z component is 0. And so the only non-zero components that we'll have, because v is in the xy plane, and so we'll have the only non-zero component is in the k-hat direction, and that's going to be the partial k-hat times the partial of minus x e to the y with respect to x, which will be minus e to the minus y, minus the partial of e to the minus y with respect to y, which will be minus e to the minus y, and that's equal to 0. So we verified that the curl of a gradient of a scalar field is equal to 0. The gradient has no rotation involved. So we've shown you, so we've gone through how to apply a divergence curl or gradient of multiple fields, and we've looked at how to apply multiple operations on a single field. Now let's try to go sort of the other direction. Let's start off with a sort of elongate version of a multiple operations. So here we're just going to have let's say theta is well, let me use t. So t is a scalar field. Actually, maybe I shouldn't really tell you. So let me just write out this equation. So we have the partial derivative of t with respect to time. We have a constant kappa, and then we have the second derivative with respect to x plus the second derivative of capital T with respect to y plus the second derivative of t with respect to z minus the quantity Vx, so it's the x component of a vector field, times the partial of t with respect to x, plus Vy times the partial of t with respect to y, plus Vz times the partial of t with respect to z. So I've written out all these derivatives. Let's express in a more compact form using our del operator. Okay, so let's figure out how to do this. So the left-hand side is not a spatial derivative, it's a partial time derivative. And then we have kappa, which is going to stay the same. And you might recognize that we have second partial derivatives with respect to each of our three components, each of our three directions, I should say. So you might recognize that as a Laplacian of t, where t is, again, a scalar field. Okay, and so that's this first term. And then we're going to subtract another term in parentheses. And you might recognize this as, so we have a vector, Vx, times the partial of t with respect to x, the y component of a vector times the partial of t with respect to y, plus the z component of the vector times the partial of t with respect to z. And you might recognize that as Vxi hat plus Vyj hat plus Vzk hat dotted with the partial t with respect to x in the I hat direction, plus the partial of t with respect to y in the j hat direction, and so forth. So I hope you can see that this is a dot product between this vector and this vector. And we can write that dot product as the dot product between a vector, v, okay, and this is the gradient of t. Right? The partial with respect to each of the directions times the unit vectors in those directions. So the more compact form of writing this long equation is this. And you'll save a lot of pen and paper if you start being more comfortable with using these del operators. Okay, so I think that I'm going to end here with this discussion of combinations of operators.